Okay. Welcome to our CAE Associates webinar presentation of the ANSYS SpaceClaim Direct Modeler. If you're unfamiliar with SpaceClaim and its products, it is a partner with ANSYS Incorporated that will allow you to take a different approach to solid modeling from what we're traditionally used to. It works in conjunction with the ANSYS Workbench environment, which we will demonstrate today. And hopefully we'll give you an idea of what direct modeling is all about in terms of the way you can manipulate geometry, create your own geometry within the SpaceClaim environment, and prep it for your meshing purposes on the Workbench side. So very simply, SpaceClaim has its own standalone interface. I'm currently running, as you can see on the top of the screen here, the ANSYS SpaceClaim version. This can be purchased via ANSYS and can be downloaded from the ANSYS customer website. SpaceClaim is a fully functional modeler. It's what's referred to as a direct modeler, and you'll see how that manifests itself throughout the webinar. It's a little bit different than what most of us are used to in terms of feature-based modeling, where we define a function and then specify parameters associated with that function on the fly. SpaceClaim is a little bit more interactive. We're working directly with the geometry. Essentially, for starters, we can begin by creating a new design. You can use SpaceClaim as a direct modeling tool. You don't need to have a CAD system to supply geometry, but then you can also, as we'll see shortly, bring CAD geometry in directly and operate on that as well. So from a modeling standpoint, the operations are fairly simple and straightforward. You begin with a plane. You can sketch 2D geometry in that plane, and then you have a series of operations like the pull or the move operation that allow you to grab that geometry and stretch it or move it. Pretty simple and straightforward as far as modeling. I can create planes by picking on surfaces, create a sketch in that plane, and the pull feature in this case will allow me to, if I create a pull in the positive direction, create a boss in the geometry, or in the negative direction, will actually create a hole or a cut type of operation. These features are fully parametric and morphable. If I select that hole, for instance, I can choose to move that hole around now, either in a tangential, or in a translational direction, or even in a rotational direction. We can change the direction or orientation of the hole. One of the nice things about this modeling environment is it's very easy to take a step back. You have a full undo and redo set of operations that allow you to correct any initial issues that you had. So we can place our hole right back in the center. If we wanted to remove the hole, or if we found there were features that we needed to take out, the fill operation will do that for us very quickly. Pick on that surface, and you can remove it. So very functional as a standalone modeling tool. There are some detailing tools available that allow you to dimension and make sketches of the geometry. There's a pretty useful set of measuring tools that are available, and we'll take use of those in a moment when we start talking about repairing CAD tools. In addition to that, we can do some repair operations like merging faces, closing up gaps, or recreating missing faces to stitch up a geometry. And then lastly, we can then prepare that geometry or take it into a finite element modeling tool, in this case the ANSYS Workbench environment. So you'll see tools up here such as extracting mid-surfaces, creating spot welds, removing rounds and faces, all the types of defeaturing operations that we typically do when we're getting our geometry mesh ready. So that's just a quick intro to SpaceClaim as a standalone modeler now. What I'd like to do now is close up this design and show you one of the main benefits of the SpaceClaim environment, that being that you don't require a CAD system to read CAD geometry. So we can create, essentially, or open up a parent CAD file directly. You'll notice here on the list that we have a variety of different commercial CAD tools that are available to us. We're going to start out with a SolidWorks file for today's demonstration. So we'll start out with this solid assembly, open it up. Now it is reading that geometry, it's reading that parent SolidWorks file. It did not use SolidWorks to do this. I do not have to have SolidWorks on the machine that I'm using to run SpaceClaim. So that's a fairly significant advantage in that you have the ability to bring into this environment many different types of CAD formats without having to have a license of that CAD tool. So we have a fairly simple example today, just kind of a bolted connection. What we're going to do is begin by defeaturing this geometry a little bit. We're going to take it into the Workbench environment, set up some boundary conditions, and run an analysis. Then we'll come back into SpaceClaim, and we'll show you how easy it is to modify or morph that geometry and then have that updated as well in the Workbench environment. Now, SpaceClaim I find is particularly useful for doing repair operations. One thing you'll note in this particular geometry is that my bolt is a little bit oversized. It's actually too large for the hole in the tap section of my connector. So one of the easy things to do here is to simply hide the connector itself. And let's take a look at what the diameter of that bolt is. So I go to my Measure tool, click on Measure, and it gives you a fairly comprehensive measurement of any of the geometry that you select. So in this case, the item of interest here is the diameter of my cylinder, which is 5 millimeters. If I show the pin and measure the diameter of the hole that the pin is sitting in, I'll see that it's 4.5 millimeters. So I'll need to correct the size of the bolt so that I can take care of that interference that happens initially in that geometry. Well, fairly easy to do on the SpaceClaim side. I can simply grab this surface, go to my Design Tools, and just pull it into the correct diameter. So I'll grab that surface, and I can either shrink it or extend it, and I'll make that 2.25 millimeters to match the 4.5 millimeter diameter of the hole. So now we have the surfaces fully aligned, and this will work very well when we generate a contact interface on the Workbench side for our analysis. A couple of other things of note. You'll notice that the bolt is fairly short. If this were a tap side of the hole, there would not be too many threads of engagement there, and we may want to extend the bolt. And again, very simply, pick on the end of the bolt and use the pull tool to stretch the bolt as far as we need to go. So we can either do it arbitrarily by just dragging the mouse, or I could specify that I'd like to see it moved 5 millimeters over its original length. The top of that bolt head looks a little funny to me, so I'm going to take advantage of the pull tool again. I'm going to, excuse me for a moment here, I'm going to grab the top surface of that bolt and pull it downward, and we'll make it 2.5 millimeters in height. And that looks a little bit more reasonable to me from a fastener standpoint. Okay, so I've got my bolt and my diameters corrected. Before I take this into the analysis environment, since I'm really looking for bulk stiffness in this case, I'm going to want to remove some of these additional features like these fillets. They're going to create some additional complexity during the meshing process while providing no real benefit in terms of the analysis result. So I'm going to go ahead and remove these fairly easily here in SpaceClaim. If I pick on one of those surfaces, SpaceClaim has a really nice selection tool that allows me to, based on a particular set of selected geometry, grab additional geometry that is of the same size or smaller. So you'll see my options here under rounds. I can grab all rounds equal to that radius, or all rounds equal to or smaller than that radius that's currently selected. So we'll pick on the first option, and you'll see that it highlighted all of the additional rounds that it found that were 1 millimeter in radius. With all those selected, you can simply go to the fill operation, pick on fill, and remove those in one shot. So very, very quick and easy way defeaturing capabilities inside of the SpaceClaim environment. A couple other things we may want to do here. This little chamfer isn't going to do much for us, so we'll take care of that as well, picking it directly, using the fill to fill it. And then for our demonstration purposes, there's no real need to have a shaft of this length, so we're simply going to grab that and shrink that up a little bit. And again, this can be done arbitrarily or by specifying a parametric value during the operation. So that being done, we're now ready to bring this geometry into the Workbench environment. That's done by going to the Prepare tab, and you can run the Workbench environment directly by picking on the icon for version 12.1. Or if you happen to have Workbench running and you've run it as a standalone, you can simply grab an analysis system, drop it on your page, and indicate that the geometry is going to be imported from the active SpaceClaim document. We'll pick on that. We'll go to Model and Edit. That'll open up the mechanical environment. And we'll see the geometry transferred over from SpaceClaim. So here's our geometry read into Workbench. From a Workbench standpoint, it's the same as geometry that was read from Design Modeler or another CAD system. We get a geometry with our parts and our names. We get a contact region between the bolt and the bracket. And we have the ability to put in some mesh operations. I like to have a nice hex mesh in my bolt, so I'm going to take advantage of a new version 12.1 feature and insert a method on the bolt itself. And we'll instruct the Workbench environment to use a multi-zone meshing technique, which will subdivide the bolt up into hex meshable volumes and give me a nice brick mesh in that region. So we can generate the initial mesh. Again, this is all pretty standard Workbench stuff. It's working directly with that SpaceClaim geometry in the same way that it would with geometry from any other tool. We can apply mesh controls and the like. So let's put some boundary conditions on this part. I'm going to make the assumption here that I'm clamping down on a very rigid pipe section. So I'm going to start out by putting a bolt pretension on the diameter of the bolt. So we'll insert a bolt pretension load, 500 pounds. That's going to be clamping down or grabbing a very rigid pipe section. So we're going to insert a compression-only support in this case to emulate that. So we're essentially getting a rigid to flexible contact surface by virtue of the compression-only support. And then to stabilize the system, we're going to add in a fixed support on the bottom face. So here's our boundary conditions ready to go, our bolt pretension, compression-only support, and fixed support. And now we'll add in some result quantities to take a look at the response of the system. So we'll go in and we'll insert a directional deformation in the Z direction. I'd like to scope that to my bolt body so that I can see where the bolt pretension is occurring. And then I'll add in a second directional deformation for the entire system in that Z direction so we can see the closing up of that gap between the two flanges. In addition to that, let's add in a few more stress results or stress contours. We'll put in von Mises stress. We'll take a look at the von Mises stress in the clamp body, and we'll also put in the contact tool. And under the contact tool, we'll select geometry by pick, and we'll take a look at what the resulting contact pressure is occurring in that region between what we're considering to be the rigid pipe and the clamp. So we're ready to go now. We go ahead, generate our solution here. And we'll take a moment for this to solve. This is a nonlinear analysis by virtue of the fact that we're using the compression-only support. As I mentioned previously, that is using a rigid to flexible contact region. Taking a look at our result now, we can see it's always a good idea to put your nonlinear results in true scale. What I'm looking at here is the vertical deflection of the bolt shank due to the bolt pretension. And we can see where the bolt pretension direction changes, and that's just above the bonded contact region. What I was really after here was to make sure that my bolt pretension did not occur in the overlap between the bottom or the tap section of the hole and the bolt. So it looks like my bolt pretension is in the right location. It's not going to be interfering with any of the bonded contact, and I should have a valid result here. In addition to that, we can look at the vertical or the crushing deformation of the clamp. So we're looking at a fairly small amount of deformation here for that 500 pounds of preload based on the stiffness of the part being pulled downward or around that rigid pipe. We can show how that manifests itself in terms of a contact pressure. You can see we have a fairly uniformly distributed pressure except for one region, and that region is being affected by the proximity of the bolt to the flange. The bolt flange is actually, the bolt itself, the hole is cutting in to the clamped region. So we can see we have a little bit of a discontinuity there in that contact pressure. In a clamping situation like this, ideally we'd like to have as uniform a pressure as possible, and we may need to make some changes to our geometry to accommodate that. So just very quickly, I'm going to put in some probe items so we can kind of see what the distribution of that pressure is around the surface. So we're varying from around 1,100 to about 2,000 psi pressure until we get over to this region here where we have a fairly spiked pressure on the side and a low pressure in between where that bolt cutout is. So let's say that in this case we'd like to improve this contact pressure distribution. And we're going to do so by trying to move that bolt further away from the actual clamped region. That can be a little bit difficult to do depending on the way that we've modeled this. If it was a feature-based parametric model, we'd have to be sure that we had sufficient parameters defined to be able to accommodate that. In the case of SpaceClaim, it's very, very easy for us to simply return to the SpaceClaim modeler and just move the bolt away from the hole. So we'll do that by first moving these flanges. We'll go back to our design tool. We will pick on these two surfaces right here, and we will pull them out by an arbitrary amount, or in this case, we'll specify that we're going to move them out by 6 millimeters. Okay, well now here comes the interesting part. How am I going to move all this complex geometry around the bolt hole? It's actually going to be quite simple with SpaceClaim. We're going to go back to the structure here. We're going to hide the bolt for a moment, and we're going to grab some surfaces. So we'll pick on the bolt surface on the top. We'll pick on this round on the outer face, and we'll grab the bottom bolt surface. We'll use our move function, which will allow us to stretch or move all of those surfaces along the flange. So as I move this away, you can see it's pulling away from the clamped region of the system. So we're going to move that, let's make it 4 millimeters. And then to place the bolt back in its correct location, we'll simply grab the bolt as a body, use the move tool again, begin to drag it, and also move that 4 millimeters to make sure that they're fully aligned. So very quick and easy way, very simple as far as modifying that geometry, getting your next iteration ready to go. So let's take this now and analyze it. So what we'll do is we'll save a copy of this. We'll call it webinar pin 2. And then when we return to the Workbench environment, we'd like to keep a copy of the original model so that we can compare with the new result. So we'll right-click on our model. We'll duplicate it. And then under the geometry here, I'll sever this geometry link. And I'll associate this new analysis with the current Webinar 2 geometry that I just created. So we can now open up another, we'll now open up a second window of the mechanical tool, and that will read in the new or the modified SpaceClaim geometry. Okay, so here's our new mechanical window. You can see that our geometry is updated. The bolt has been moved. And one of the nice features here is that all of our boundary conditions and our mesh controls are already reassigned to the new geometry because we made a duplicate or a copy of the original analysis. So the only thing I have to do here is simply click on the Solve button, and we're ready to generate the result for this new geometry. And it's going through the same process that it went through previously, where it's evaluating the contact situation with the compression-only support on the cylindrical surface. And we have our result. And one of the things that we'll notice immediately is that the contact pressure is much more uniform around that region. And we can, not only is it uniform, but it is also, if we bring these two in side by side, it is also of greater magnitude than the previous case. So we'll put our two windows here side by side so we can easily compare. So we're looking at originally a contact pressure that maxed out around 8,000 psi, averaged about 2,000 psi around the cylinder. Now we have a contact pressure that's much higher at that peak point. And when we look at the distribution in and around these regions of the part, you can see that we're getting a more uniform and higher overall contact pressure in that region. So we may also need to, in this case, modify that bolt pretension and check and see if that's going to affect the design as well. So again, very, very easy to quickly modify the geometry. We can go back to SpaceClaim, do other things, pick on these faces here, and say we were to pull those out, we could change the size of the flange, we could change the location of the bolt. A whole variety of different options available to us. We can add additional geometry. We can subtract additional geometry as needed. And again, the undo, redo features are all fully functional, so you can always take a couple of steps back and repeat your process or modify it as you go. So very, very quick and easy to use. So just summing up here, some of the many advantages of the SpaceClaim Direct Modeling are: one, that you don't need to have the CAD system on your system in order to be able to import the geometry. Two, you don't need to import the parameters from the CAD tool. You have access to the SpaceClaim geometry itself or the imported geometry and you have the ability to modify that or stretch it or morph it as you will. Additional advantages, you can take these parametric operations into the parameter manager on the Workbench side of the equation, and you can drive those parametrically from Workbench once you've established the parametric features on the SpaceClaim side. In addition to that, if you were working with a non-parametric file, something like a SAT file or an IGES or Parasolid file, any morphing operations that you make on the geometry in SpaceClaim can be driven parametrically with the Workbench environment because it does associate directly with the parameter manager inside Workbench. Now at this point, I think we'll stop the recording of the webinar and we'll take any questions that you may have. So we'll bring up the